All right, so here we go. I'm going to try to bring all the main topics that we've talked about today: heat, gas laws, and in a simplistic manner, I'm going to try to explain the idea of airflow and climate. It's actually kind of cool when you think of the idea that when you have water going from the gas phase down to the liquid phase or even the solid phase, you end up giving away quite a bit of energy. And that energy is not free floating, it's actually being used by molecules to do certain activities. So think of the following. On Earth, we have the surface and there's the troposphere. Now, the troposphere is the altitude where usually planes tend to fly. Okay, so this is pretty high. It's a few miles above the surface of the Earth, but that's usually where airplanes travel. And the troposphere also contains some amount of gaseous molecules within it. Now the idea though is that the surface is going to contain higher amount of molecules, both in the solid, the liquid, and in the gas form. And the pressure on the surface is higher than the pressure in the higher altitude, because in higher altitude you have less gas molecules, so you have less pressure by default. All right, so consider the following. You have sunlight passing through the troposphere. Some of it actually gets absorbed and kind of taken away by the troposphere, which is good because certain UV rays we don't want to reach us down here. That would be bad. But some of the sunlight still makes it through. And what happens is that the sunlight, as you'll find out in future lectures, is actually heat in waveform. And the heat that's coming out and reaching us from the sun, yes, some of it is being absorbed by the troposphere gases, but the truth of the matter is that the majority of the molecules reside on the surface of the planet. And since Q equals mcat, the higher the mass content, the higher the amount of heat absorbed. What this is really telling us is that the amount of heat is going to be greatest on the surface than it is in the higher altitude. This is also the reason why when you go up hiking, to a mountain, the temperature starts dropping down more and more as you go higher and higher in the mountain. That's simply because you have less gases present in there, less molecules present to absorb heat. So you have a lower temperature. All right, now the interesting thing about it is this. We talked about the idea that ideal gas laws provides us a means for determining the density of a gas. And specifically, if you look at the equation here, density equals pressure times molecular weight over RT, the peculiar nature of this equation is that the temperature being in the denominator means that if you have a gas that is hot, the hot gas is actually going to have a lower density than a cold gas. And the reason being is because the hot gas will have a higher value of temperature. Temperature being in the denominator will make the entire density smaller. So the density of a hot gas is lower than the density of a cold gas. And from your experiences in the lab where you add a substance that is higher in density to one that is lower in density, the higher density substance tends to sink in. And so something similar happens right here. The troposphere gases that are lower temperature are technically denser than the gases closer to the surface because they are colder. And so they kind of start sinking in, and via buoyancy, they start pushing some of the hot air towards the troposphere. Okay? And because at some given temperature you will have some vapor pressure of water present, especially if you're near the ocean, you're going to have some amount of water going towards the upper atmosphere, maybe even the troposphere, due to this buoyancy effect. So you'll end up with some of these gas particles, which are hot, being pushed up to the upper portion of the atmosphere. And because the upper portion of the atmosphere has less gas particles in general, the temperature of the upper atmosphere is lower, right? So here we're looking at Gay-Lussac's law. The temperature of the troposphere is going to be lower than the temperature of the surface. So the gas particles are going to start giving away energy, right? Because Q hot is going to be giving heat to Q cold. So you're going to give away energy away from the hot substances to the rest of the surrounding. And since some of that gas present in the troposphere now is some water vapor that came along for the ride due to that buoyancy effect, you're going to end up condensing some of the water. And in a typical day, like winter, fall, what this condensation will end up looking to you is nothing more than clouds. Clouds are simply condensed water of about micrometer length or diameter. And it turns out that that diameter, light gets refracted very efficiently, and that's why we see clouds present in the sky. It's technically just water semi-condensing into small droplets. All right, that's what happens on a regular day. But let's consider what happens on summertime. In summertime, we actually get more exposure to sunlight. And the outcome of this is that as a result of having more energy being delivered per unit area during summer days, you end up with a surface that is hotter, a lot hotter now than the troposphere. They had the same idea that Q equals mcat. You have a lot more mass on the surface and you end up getting most of the heat allocated to the surface. So the buoyancy effect, due to the discrepancy in the densities of the hot air and the cold air, actually push a significant amount of the hot air via buoyancy onto the upper atmosphere, up to the troposphere. And because you had a hotter surface to begin with, that means that your vapor pressure of water is actually going to be higher than it was during a winter time or a fall time. So you're going to end up pushing a lot more water into the upper atmosphere. And as I said, in the upper atmosphere, the temperature is lower in general, so you're going to end up giving away heat from all the hot gas particles that got pushed upwards due to buoyancy. And now, since you have a lot more water present in here, the amount of heat that you are giving away is not only enough to produce condensed water in the form of clouds, but now you have enough energy giving away to produce high currents of airflow in the upper atmosphere. And basically what I'm getting at is that because you have excess water now present in your atmosphere, the moment it condenses and the moment it gives you that extra amount of energy, you are now basically creating storms, right? So here I'm showing pictures of the monsoon around Arizona and New Mexico, and here's another monsoon storm producing lightning on top of that, because now the amount of energy coming out of the condensing water is enough to actually remove electrons from various particles and gas molecules in the atmosphere, and that creation of ions in the atmosphere kind of creates a voltaic pathway for light to travel. And so that's what lightning really is. But the key idea right here is that we are yielding more vapor water in the atmosphere, and that vapor water is giving a lot more energy, yielding not just clouds, but now storms. So in essence, the storms are basically being powered by water giving away some of its heat as it condenses back to a liquid phase. And if the storm is a little bit nasty, it could actually produce hail, in which case you have even more energy given to the storm. So that would be a nastier storm. All right, now let's consider a slightly more troublesome situation. Okay, so let's say that we have a cold front of air coming from the Arctic, and we have a hot front of air coming from the tropics. It so happens that around summertime, springtime, summertime, these cold fronts happen to collide with one another in opposite directions somewhere in the Midwest of the US. There's many other places on Earth where this happens, but I'm going to focus on the US for now. So what happens is the cold front, moving to the right in this diagram, and the hot front moving to the left in the diagram, they come together and they collide. And the hot front has quite a bit of hot gas particles within it. So the moment they come in together, they basically have this huge discrepancy in density such that the cold front starts pushing the hot front all the way up into the upper atmosphere. And since they're going in opposite directions, there's a little bit of momentum that leads to slight circular motion as the hot gas gets pushed further and further and further up into the atmosphere. Now once it gets there, what you've basically done is you've provided quite a bit of water vapor all at once to the upper atmosphere. Because temperature is going to be pretty cold up there, all this water vapor is going to give away its energy all at once. And when that happens, you have so much energy present that not only do you have enough energy to create a storm, but you create a very nasty storm. In particular, I'm referring to the creation of tornadoes. Now, this is a rather simplistic outlook on how these storms get created, but you can see that some simple ideas of heat transfer and gas laws are kind of enough to rationalize some of the things that you're seeing in nature, right? Some of them are a little bit drastic, but all in all, this is all about energy. The more energy you have present in the form of vapor water in the atmosphere, the worse off you're going to be in terms of storms. So, just a little cool addendum to the idea of heat. Now, with this, I will conclude the video and I'll conclude the lecture series for lecture 10. Next stop is lecture 11, excuse me, which will be the first law of thermodynamics and enthalpy through and through. All right, so we'll stop the video right here. I hope you enjoyed it.